Removing the neutral ground bond at the generator prevents a potential hazard called generator backfeed. When the generator is operating in parallel with the utility, a fault in the utility system can cause current to flow back through the generator and out onto the utility lines. This can endanger utility workers and damage the generator. By separating the neutral ground bond, the fault current is forced to flow through the generator feeder equipment grounding conductor, which provides a lower impedance path back to the source. This limits the voltage and the generator frame and reduces the risk of electrical shock. When the generator is not connected to the load, there is indeed no fault path if the frame becomes energized. However, this is not considered a health or safety concern because, firstly, the generator is typically not used for extended periods when it is not connected to the load, and secondly, if the frame becomes energized, a fault will trip the generator's internal protection devices. Neutral floating refers to a condition where the neutral conductor is not connected to earth-ground, but is instead connected to the generator frame. This practice is often used with generators that are isolated from the utility system and do not have a dedicated neutral ground bond. Neutral floating allows the generator to isolate itself from ground faults, preventing current from flowing back onto the utility lines. However, it also means that the neutral is not grounded, which can increase the risk of electrical shock from other sources. When installing a generator with a transfer switch, understanding the neutral ground bond is crucial for safety. The primary reason for removing the neutral ground bond in a generator used with a transfer switch is to prevent parallel paths for neutral current. When the generator is connected to the system and the transfer switch is in the generator position, the generator becomes the source of power. If the neutral ground bond is still present at the generator, it creates a second path for the neutral current to return to the source, which is now the generator. This can cause several problems. Firstly, it can lead to circulating currents in the grounding system. The neutral current will split between the neutral conductor and the equipment grounding conductor, which can cause the equipment grounding conductor to become energized. This is a safety hazard, as anyone touching grounded metal parts could be exposed to this current. Secondly, it can cause nuisance tripping of ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or RFCIs. These devices are designed to detect small imbalances in current between the hot and neutral conductors. When neutral current flows through the equipment grounding conductor, it creates an imbalance that can cause these devices to trip. Thirdly, it can interfere with the operation of sensitive electronic equipment. The circulating currents can create electromagnetic interference, or EMI, which can disrupt the operation of computers, audio equipment, and other electronic devices. To prevent these problems, the neutral ground bond must be removed at the generator when it is used with a transfer switch. This ensures that there is only one path for the neutral current to return to the source. With the neutral ground bond removed, the neutral current will flow from the load, through the neutral conductor, back to the neutral terminal in the transfer switch, and then back to the generator. The equipment grounding conductor will provide a path for fault current to return to the source, but it will not carry any neutral current under normal conditions. It's important to note that removing the neutral ground bond only applies when the generator is connected to a building's electrical system through a transfer switch. When the generator is used as a standalone power source, such as at a construction site or for camping, the neutral ground bond should remain in place. In these situations, the generator is the only source of power, so there is no risk of creating parallel paths for neutral current. Now, let's address the concern about the fault path when the generator is not connected to a load or is used elsewhere. It is true that without the neutral ground bond and without being connected to a load, there is no direct fault path back to the source if the generator frame becomes energized. However, generators typically have internal overcurrent protection devices, such as circuit breakers or fuses, that are designed to trip in the event of a fault. If the generator frame becomes energized, the fault current will flow through the generator's internal wiring and trip the overcurrent protection device, disconnecting the generator from the source. Furthermore, portable generators are often equipped with ground fault circuit interrupter protection for the receptacles. These GFCIs will detect any leakage of current from the hot conductor to ground and trip the circuit, further protecting against electrical shock. It is also important to follow the manufacturer's instructions for proper grounding of the generator. This may involve connecting the generator frame to a grounding electrode, such as a ground rod, using a grounding conductor. This provides an alternative path for fault current to flow back to the source, even when the generator is not connected to a load. Now let's discuss neutral floating in more detail. Neutral floating refers to a configuration where the neutral conductor is not directly connected to ground at the generator. Instead, the neutral may be connected to the generator frame through a high-impedance resistor or may be left completely ungrounded. The purpose of neutral floating is to limit the ground fault current in the event of a fault. When the neutral is directly grounded, a ground fault can cause a large amount of current to flow through the grounding system. This can create a safety hazard and can also damage equipment. By floating the neutral, the ground fault current is limited to a much lower level. This reduces the risk of electrical shock and minimizes the potential for damaged equipment. However, neutral floating also has some disadvantages. One disadvantage is that it can make it more difficult to detect ground faults. When the neutral is directly grounded, a ground fault will cause a large voltage drop in the grounding system, which can be easily detected by ground fault detection equipment. When the neutral is floating, the voltage drop in the grounding system will be much smaller, making it more difficult to detect. Another disadvantage of neutral floating is that it can increase the risk of transient overvoltages. When the neutral is directly grounded, it provides a path for transient overvoltages to dissipate to ground. When the neutral is floating, there is no direct path for transient overvoltages to dissipate, which can cause them to build up to dangerous levels. In summary, removing the neutral ground bond at the generator is essential when using a transfer switch to prevent parallel neutral paths and associated problems. While removing the bond may seem to eliminate the fault path when the generator is not connected, internal protection devices and proper grounding practices ensure safety. Neutral floating, where the neutral is not directly grounded at the generator, is a design choice to limit ground fault current, but it also has its drawbacks, such as making ground fault detection more challenging. When dealing with electrical systems, it is always best to consult with a qualified electrician to ensure that the installation is safe and code compliant. They can assess the specific situation and recommend the best approach for grounding the generator and connecting it to the building's electrical system. This will help to ensure that the system operates safely and reliably. Remember that electrical work can be dangerous, and it is always best to leave it to the professionals. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. They can also ensure that the installation complies with all applicable codes and regulations. Understanding the reasons behind removing the neutral ground bond and the implications of neutral floating is crucial for anyone working with generators and transfer switches. It promotes safety, prevents equipment damage, and ensures the proper operation of the electrical system. Remember to always prioritize safety and consult with a qualified electrician when in doubt. They can provide expert advice and guidance to help you make informed decisions about your electrical system. The equipment grounding conductor, or EG, plays a vital role in electrical safety. It provides a low impedance path for fault current to return to the source, which helps to quickly trip over current protection devices and prevent electrical shock. The EGC is typically a green insulated wire or a metallic conduit that is connected to the grounding electrode system at the service entrance. It runs along with the circuit conductors and is connected to the metal enclosures of electrical equipment, such as outlets, switches, and lighting fixtures. In the event of a ground fault, the fault current will flow through the EGC back to the source. This will cause a large amount of current to flow through the circuit, which will quickly trip the circuit breaker or fuse. This will disconnect the power to the circuit and prevent electrical shock. The EGC also helps to equalize the voltage potential between different metal parts of the electrical system. This prevents voltage differences that could cause electrical shock. For example, if a metal water pipe is not properly grounded, it could have a different voltage potential than the metal enclosure of an electrical appliance. If someone touches both the water pipe and the appliance enclosure at the same time, they could receive an electrical shock. The EGC helps to prevent this by ensuring that all metal parts of the electrical system are at the same voltage potential. The size of the EGC is determined by the size of the circuit conductors. The larger the circuit conductors, the larger the EGC must be. This is to ensure that the EGC can safely carry the maximum fault current that the circuit is likely to experience. The EGC must be properly installed and connected to ensure that it provides a reliable path for fault current to return to the source. All connections must be tight and corrosion-free. The EGC must also be protected from physical damage. In some cases, the EGC may be required to be installed in a conduit or other protective enclosure. Ground fault circuit interrupters, or GFCIs, are another important safety device. They are designed to protect people from electrical shock by detecting small imbalances in current between the hot and neutral conductors. GFCIs work by monitoring the current flowing through the hot and neutral conductors. If there is a difference of more than a few milliamperes, the GFCI will trip the circuit and disconnect the power. This can happen if someone is touching a live wire and ground at the same time. The GFCI will detect the leakage current and trip the circuit before the person can receive a serious electrical shock. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas. They are typically installed in outlets or circuit breakers. It is important to test GFCIs regularly to ensure that they are working properly. This can be done by pressing the test button on the GFCI. If the GFCI trips, it is working properly. If it does not trip, it should be replaced. Arc fault circuit interrupters, or SIs, are designed to protect against fires caused by arc faults. Arc faults are dangerous electrical faults that can occur when electricity jumps between two conductors. This can happen if the insulation on a wire is damaged or if a connection is loose. Arc faults can generate a lot of heat, which can ignite nearby combustible materials and start a fire. SIs work by detecting the unique characteristics of arc faults. When an arc fault is detected, the SI will trip the circuit and disconnect the power. SIs are required in many locations such as bedrooms and living rooms. They are typically installed in circuit breakers. It is important to test SIs regularly to ensure that they are working properly. This can be done by pressing the test button on the SI. If the SI trips, it is working properly. If it does not trip, it should be replaced. Electrical codes and standards provide detailed requirements for the safe installation of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association, or NFPA, and the International Association of Electrical Inspectors, or IE. The most widely used electrical code in the United States is the National Electrical Code, or NEC, which is published by the NFPA. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. Electrical codes and standards cover a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. They are designed to protect people and property from electrical hazards. It is important to follow all applicable electrical codes and standards when installing or working on electrical systems. Failure to do so can result in serious injury or death. Permits and inspections are often required for electrical work. This is to ensure that the work is done safely and in compliance with applicable codes and standards. A permit is typically required before any electrical work is started. The permit application must include detailed information about the proposed work, including the location of the work, the type of work to be done, and the materials to be used. Once the permit is approved, the electrical work can be started. After the work is completed, it must be inspected by a qualified electrical inspector. The inspector will verify that the work was done in accordance with the applicable codes and standards. If the work passes inspection, the permit will be closed. Working with electricity can be dangerous. It is important to take precautions to protect yourself from electrical shock. Firstly, always disconnect the power before working on any electrical equipment. This can be done by turning off the circuit breaker or removing the fuse. Secondly, use insulated tools. Insulated tools are designed to protect you from electrical shock. Thirdly, never work in wet conditions. Water is a good conductor of electricity, so working in wet conditions increases the risk of electrical shock. Fourthly, be aware of your surroundings. Look for any potential hazards, such as exposed wires or damaged equipment. Fifthly, if you are not comfortable working with electricity, call a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. Proper grounding is essential for electrical safety. Grounding provides a path for fault current to return to the source, which helps to quickly trip over current protection devices and prevent electrical shock. The grounding system consists of the grounding electrode system and the equipment grounding conductor. The grounding electrode system is a network of conductors that are connected to the earth. This network provides a low impedance path for fault current to return to the source. The equipment grounding conductor is a conductor that connects the metal enclosures of electrical equipment to the grounding electrode system. This conductor provides a path for fault current to return to the source in the event of a ground fault. The grounding system must be properly installed and maintained to ensure that it provides a reliable path for fault current to return to the source. All connections must be tight and corrosion-free. The grounding system must also be protected from physical damage. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when a circuit is carrying more current than it is designed to carry. This can happen if too many appliances are plugged into the same circuit. A short circuit occurs when there is a direct connection between two conductors of opposite polarity. This can happen if the insulation on a wire is damaged or if a connection is loose. Overcurrent protection devices work by interrupting the flow of current in the circuit when an overload or short circuit occurs. This prevents the circuit from overheating and causing a fire. Circuit breakers are resettable overcurrent protection devices. They can be reset by turning them off and then back on. Fuses are non-resettable overcurrent protection devices. They must be replaced after they have been blown. The size of the overcurrent protection device is determined by the size of the circuit conductors. The overcurrent protection device must be sized to protect the circuit conductors from overheating. Understanding electrical concepts is essential for anyone working with electricity. Some of the basic electrical concepts include voltage, current, resistance, and power. Voltage is the electrical potential difference between 2 points. It is measured in volts. Current is the flow of electrical charge. It is measured in amps. Resistance is the opposition to the flow of electrical current. It is measured in ohms. Power is the rate at which electrical energy is transferred. It is measured in watts. These concepts are related by Ohm's law, which states that voltage is equal to current times resistance. Understanding Ohm's law is essential for understanding how electrical circuits work. Series and parallel circuits are two basic types of electrical circuits. In a series circuit, the components are connected in a single path. The current is the same through all of the components in a series circuit. The voltage is divided among the components in a series circuit. In a parallel circuit, the components are connected in multiple paths. The voltage is the same across all of the components in a parallel circuit. The current is divided among the components in a parallel circuit. Understanding the difference between series and parallel circuits is essential for troubleshooting electrical problems. Troubleshooting electrical problems can be challenging. However, there are some basic steps that can be followed to help identify and resolve the problem. Firstly, identify the problem. What is not working properly? Secondly, gather information. What are the symptoms of the problem? Thirdly, analyze the information. What could be causing the problem? Fourthly, test the possible causes. Use a multimeter or other test equipment to test the possible causes of the problem. Fifthly, repair the problem. Replace any faulty components or make any necessary repairs. Sixthly, test the repair. Make sure that the problem has been resolved and that the circuit is working properly. Regular electrical maintenance is essential for ensuring the safety and reliability of electrical systems. Some of the basic electrical maintenance tasks include inspecting electrical equipment for damage, cleaning electrical equipment, tightening connections, and testing overcurrent protection devices. Regular electrical maintenance can help to prevent electrical problems and extend the life of electrical equipment. When selecting electrical equipment, it is important to choose equipment that is appropriate for the application. Consider the voltage, current, and power requirements of the equipment. Also, consider the environmental conditions in which the equipment will be used. Choose equipment that is designed to withstand the environmental conditions. It is also important to choose equipment that is listed by a recognized testing laboratory, such as Underwriters Laboratories, or all. Listed equipment has been tested and certified to meet safety standards. When installing electrical equipment, it is important to follow the manufacturer's instructions. Also, follow all applicable electrical codes and standards. Proper installation is essential for ensuring the safety and reliability of electrical equipment. If you are not comfortable installing electrical equipment, call a qualified electrician.